All right, let's get started. Before introducing our speaker today, let me remind you of some of the events at the center next week. On Tuesday, my HPS colleague, Colin Allen, will be giving a talk on AI, or precisely on large language models, whether they are smart or not, intelligent or not. Will should be an interesting talk. And on Friday next week, we are back to philosophy of physics, or to physics, with a talk by David Slow. If you want to hear more physics, come back next week on Friday. I should also mention that this seminar is a bit unusual in the following way. It's co-organized with the seminar series of the RACI, which is a research, ethics, and society initiative, which is led by my colleague Lisa Parker, and which is under the Office of Pitt Research. The RACI fosters awareness of the ethical, legal, and social implications of the research which is conducted at Pitt, and it offers consultation service in research ethics. There will be a talk on April 14 at noon online as the next talk of the RACI by Lee Fisher about the ethics of obtaining consent in the studies involving neuroprosthetic devices, things you put in your brain. So that's to be the next event organized by the RACI. Today it's my wonderful pleasure to introduce Sergey Frolov, which I met online now a year ago in a series called Data Laws, organized by the library at Pitt, about the significance of data for many sciences. And I heard Sergey's talk, and I was really incredibly impressed and amazed and shocked. We need to bring that back to the Center for Philosophy of Science, that he can talk to some of my colleagues. Thanks for accepting our invitation. And at the same time, Lisa had a very similar idea, so we just joined this. Now, Sergey is an associate professor in the Department of Physics and Astronomy at the University of Pittsburgh. Since I do mostly philosophy of psychology, cognitive science, and neuroscience, he works in areas in the world that are very mysterious to me. But mostly, as I understand, in insulated particles.
Also to me.
Also, well, that's actually a good insulated particle physics is published extremely widely. It's the best journal in science, including the journal Science and the many journals of Nature. And it's also won many prizes, including a few years ago an NSF Career Award. So congratulations and thank you for coming today.
Thanks so much, Edward. Thanks for mentioning the Love Data Week, which is I guess an international event, but also organized at Pitt by the library. And Dominic here is the key organizer, and I guess even the second time in a row they wanted to sort of co-feature this talk, so it's also co-featured there, and I'll try to reflect that in what I talk about. This has been my first slide for almost a year, and I hope to at some point stop showing it, but I had to keep starting every talk I give, no matter the topic, with this same slide. And the pictures are almost 1 year old, sort of March 2022. One of the physics institutes, a world famous institute in Kharkiv, which has a long history in physics, also has a nuclear reactor there, of course, because, you know, what else would Russians bomb? And this one is a paper on a topic that my group works on, nanowires, and I've learned from this paper more than 10 years ago when it came out, and I tried to work with these people. So this is just to highlight the fact that Ukrainian science does make contributions to the world science, and you know, as soon as the war ends, I hope that comes back with force on the world stage. And this is my own group, not so far from here at the University of Pittsburgh. You can see my building from this window. And if you visit, and you're all welcome, of course, you will see all these machines which are low temperature making machines, dilution refrigerators that create extreme conditions like close to absolute zero temperature and extremely high magnetic fields to reach the quantum regimes where quantum effects dominate and manifest. And this is my group, a picture taken last week where we were taking a day off work to take care of ourselves a little bit in the spirit of the year of well-being at the University of Pittsburgh. So the talk is co-sponsored by 3 very different centers. And it was a genuine challenge for me to predict what the audience will be like and what you would know and not know and what would you like to hear about. And also, I could take this story in so many directions, talk about my personal experience, retracting papers from Nature and, confronting colleagues and institutions about how the scientific process works or doesn't work. And the bigger implications of this and other things about how to do it better through data sharing, etc. So it was a difficult choice, and I have decided to just talk about all of it in the course of the next, half an hour, 40 minutes. And when I thought about how could I talk about all of it and how could I unite it all under one umbrella, I thought about this paper. This is a paper published just a few months ago in October 2022. And it's a paper in my field from a group of Professor Hao Zhang at Tsinghua University, a world-renowned science center. And it talks about, so the first half of the title is an electrical signal in a specimen, which is a little electrical circuit based on a nanowire. And it talks about this signal being very close, within 5%, as they highlight in the title of the paper, to a fundamental value, which is comprised of the fundamental constants of our universe, the electronic charge, and the Planck constant, which defines the energy scale of quantum effects. So you can see how, relating your measurement in a circuit to something so fundamental could be of interest to a renowned journal. And I can also say for what's coming is that this claim has strong relevance and strong suggestive power in the research topic that I focus on, which is Majorana fermions, that I'll tell you about in a moment. But before that, I know some of you are very familiar with physics and some of you may be less familiar. Let's set the stage and recap what physics is. Why not? So let's talk about physics through this paper. This paper is published in a journal called Physical Review Letters, which is published by the American Physical Society, which is a society that was established in 1899 when many of the societies emerged. And the primary goal of this society to begin with was to communicate, facilitate interactions between physicists. At some point in their history, they took on the role of publishing, and they took control over Physical Review, which was at the time one of the prime journals. American Physical Society is now a very large society and a very influential one with tens of thousands of members, something like 65 or 1,000 members. And the history of physics itself for the last century is reflected in what Physical Review was communicating about. So this is a very big deal. Until 20 years ago, when a lot of physicists simultaneously figured out that they could publish their things in Science and Nature, this was the journal that you have to be in this journal. You don't even want to, but you have to, right? To be a physicist, to have opportunity to discuss. Okay, so let's take this journey and remind ourselves what physics is
and I hope this will speak for itself. It will be a virtual stroll through the history of physics that Physical Review put themselves together on this website. And, just to facilitate it, it's actually not a stroll, it's a scroll. You have to scroll down here, but I didn't want to mess with switching between browser and PowerPoint. So I scrolled through it and made a video. And so as the video will be playing, you will see from the start of this society how they themselves, the American Physical Society, highlight these milestones in physics that many of you will have heard of: particle wave duality, Onsager principle, Einstein's paradox, quantum electrodynamics, scrolling too fast, superconductivity, expansion, the inflation of the universe. What is there? Oh my God. So these are quarks, Weyl fermions, quantum Hall effect, entanglement, Nobel Prize of last year, high temperature superconductivity, LIGO, and Weyl fermions, topological insulators, and so on. So, this is what they themselves highlight. And of course, in 2022, they published that paper about the signal approaching quantized conductance, and it has to do with Majorana. And let me tell you about that, because this story fully deserves to be on that list that we just took a virtual scroll through, because of so many dimensions that it has. Just from the historical point of view, this person, Ettore Majorana, his biography is amazing, and he eventually disappeared, and we don't even know what happened to him. But he's a genius of theoretical physics. Admitted by people like Enrico Fermi to be one of the brightest minds of his time. Didn't like to publish much, but he did publish a few papers. And so one of the things he did was he was solving, playing with this thing called the Dirac equation. Dirac equation is a very important equation that combines quantum theory and the theory of relativity, arguably the two biggest foundational theories in physics, into one equation, and was demonstrated to have enormous predictive power over things that we might see. So, for instance, the existence of antimatter was deduced from solutions to this equation. And so it became sort of accepted that any solution of this equation is or could be a particle in this universe. And so Majorana found a very special solution that would be a particle that is its own antiparticle, described by this equation, and this is like maybe the only equation I'll have in my talk, so don't worry. And so this is already a very intriguing thing. What a particle that is its own antiparticle, what we know is that, if the particle and antiparticle meet, they annihilate. So what happens if a particle meets itself? Does it self-annihilate? You already start to think about all the interesting things about it. And indeed, it's a paradoxical particle at many levels. Try to capture it in this René Magritte painting, which somewhat speaks to the peculiarity of this particle. Or in the background, you have this tennis ball that's submerged in water in exactly halfway, where the object and its reflection make a whole object. And so matter and antimatter is like the image and the reflection. And so these are two very good analogies. It goes beyond that in terms of spookiness or weirdness. And I'll talk to you about this in a moment. So if you visualize the solutions of the Dirac equation, they're kind of a cone. They're a cone in energy and momentum, but it's a cone. And the upper half of the cone, like it's a double cone, the upper half of the cone is matter, and the bottom half is antimatter. And so where you look for a particle that's matter and antimatter is at this unique point, special point, sometimes called the Dirac point, where matter and antimatter meet. And of course, this goes back to these historical works, but Majorana particle has not been found in the wild, in space or in accelerators or in detectors. So what we do in my lab, which fits in a reasonable size like this size room over in physics, is recreate this math, these equations, but in an electrical circuit. And so that's what a lot of us do in my field of condensed matter physics. It's called creating quasi-particles. So in condensed matter, in a circuit, this goes much beyond what even Ettore Majorana himself invented, right? And this is just a list of, actually, it's not a list of properties, it's a list of missing properties that these objects are expected to not have. And if you just look at this list, you can get dizzy, because what is it? What it even is? It has nothing. It has no mass, no magnetic properties, no electrical properties. In fact, it's called a fermion, but it is not a fermion, so it's not in that class of particles altogether. I already mentioned it's not an actual particle. It's actually a quantum mode. So you can reach enlightenment just by thinking about what this means. Right? So if you're familiar with the Higgs boson, which is sometimes referred to as a God particle because it ties together the standard model of matter, this would be a Zen particle. And indeed, very smart people thought about what this means for a long time, and they took it very, very, very far, in their minds. None of this exists. Oh, sorry, didn't want to click that. I was still here. None of this has been realized, but this is the idea that drives a lot of this research, in fact, is the idea that if you had these objects sort of littering a plane, you had a plane and a lot of these Majoranas in the plane, and you could control their positions. You could move them around and keep track of which order you swap them. Kind of like this evolution in time, and you keep track of the world lines, the trajectories in space and time, the two-dimensional space, and the third dimension is time. You could store and do logic operations on information that's encoded in the positions of these particles. So they're distinguishable particles, which is very bizarre for quantum particles, which are, all the rest of them are indistinguishable. And this became known as a blueprint for topological quantum computing, because in fact, the information that you can store and manipulate this way is quantum. And so the entire, I'm not going to talk about quantum computing here in the interest of truncating the discussion, but if you've heard anything about it, or if you haven't, I encourage you to, look it up. Okay. So with all that, about 10 years ago, I was still a postdoc in the Netherlands, and there were these predictions that you could do this with nanowires, and we did this experiment where we found pretty strong signatures, although we still were careful and we described it as signatures. And this is our paper from 10 years ago on signatures of these fermions in nanowire devices. This is the cover. It went to the cover of Science magazine. And this is a device. And, this is a Star Wars version of the device where this is a nanowire. And there's context to it, so it's an electrical experiment where current is flowing from the golden electrodes into the blue, and there are all these control parameters, and the Majoranas were supposed to emerge here. And we had some concerns about some of the data, not fully fitting the theory, and we wanted to follow up. But by and large, it was sort of a pretty strong evidence, and not just us, but everybody said. Even when I expressed concerns, people would tell me, relax, you got it, you made it, enjoy it, push it forward, go for it, let's move on, and that's what we did for a while. And okay, all these logos, right? This just to impress you on purpose, how big it became. And, of course, because of the quantum computing connection, but also because of all the fascinating, mysterious indeed physics that I sketched for you. So, it's gotten really, really big. And so, yes, of course, what else could I couldn't even get funded to do anything else. So when I came to Pitt, this was all my research was about this, and we got a lot of money to study this, and we kept trying to push it forward, and it wasn't sort of going forward. And us and other people realized at some point, a few years later, that there is another effect, another explanation that captures perfectly everything that has been observed so far. An alternative, very potent one. But in the meantime, the field grew, and here's there was some background, theory work, Majorana, and then this is our first experiment, and then it started to explode, and I think it still keeps growing. This graph is a year old or so, but just by the number of papers, you can see this is a major activity. And somewhere on the middle of that hump, this experiment came out, and then it was sort of understood what it meant over the next 2 or 3 years. But basically, this is a paper, not our paper, but another paper from the same early era that published this signal. Here is the signal. It's called the zero bias peak, the same as in the title of the 2022 paper that I started with. It is a little peak in an electrical signal at the 0.0 source drain applied voltage, which exactly where you expect a Majorana to be. And then this is a signal that other than the color plot, they even rotated it by the same 45-degree angle so that it looks similar. A very similar signal, but has a demonstrably totally different origin. And so where this was attributed early on to Majorana, this was absolutely incompatible with Majorana. It was something else. Okay, so the implications of this are that, well, the measurement technique needs to be refined to tell the difference between the two. The samples, the nanowires, need to get better, cleaner, so that this occurs less frequently, and we have a chance to see sort of the golden tree in a weeds in the forest, to see this affect the Majorana. This was all sort of already becoming clear, especially to the people who were experts and doing this every day in their labs, 5 or 6 years ago. But the claims kept coming. The claims of Majorana, its new properties being uncovered, getting better, samples getting better. This just kept on going. And at some point, I found myself in a situation where my own students, my own research, we were trying to be careful, refraining from publishing or publishing detailed and nuanced papers. And then I would give a talk and show our data, and somebody in the audience would say, but wasn't this already demonstrated? Why are you worried about this? This was done, right? The problem's solved. There's Majoranas, they look really good based on these other published papers. And at some point, it reached such a threshold that I found our little program surrounded by this very powerful movement where, everybody else was convinced that the problem is solved, and I was convinced that nothing was solved. And at some point, I looked at the next paper that came out, and I said, no way, this cannot be. What they're saying cannot be. And I steamed on it, and I sort of built up momentum, or how you want to call it. And I asked for them for data. I asked them for data, and I still had connections. This was my old group where we did the original work in the Netherlands, and they shared some data with me. And this what happened. Fast forward 3 years, that paper became retracted from Nature. Oh. One more paper from the same group got retracted, and through my work and the work of my colleagues, and we recommended even more papers to be retracted from similar high journals. So here's one example where this is Science, this is another group, but the similar topic where we got a little bit of data, and by comparing what is in the paper to what is in the data, we made, I think, a very strong case that the paper should be retracted, but current stage is editorial expression of concern. And there is an investigation going on, so I guess we will see what happens with this paper. Now, to put it in context for you, when this first retraction happened, all kinds of news stories came out again, you know, the BBC, the Wired, Gizmodo, and I guess one of these, BBC or something, had a fact that 88 papers were retracted from Nature in the entire history of Nature. So this is, you know, this I guess was 89, and this was number 90. So this is not, you know, and then not, you know, there's one more other group, as far as I know, where more than one paper was retracted from Nature. Also in our field, by the way. So the famous Sean scandal.
If that watermark actually appears in the journal itself, if I were to go there?
Yes, to their credit. Yes. Yes. That's the sort of the least they can do, right? I wish only the watermark appeared. Nothing else. Okay, so just to give you an understanding of what the problem was with these papers, it's we all familiar that there are scandals when somebody just makes up data, and we all understand that's not appropriate. You know, you publish an experiment, but you drew the data in Photoshop. That's not good, right? Some of us feel that that's the only crime. Everything else is interpretation. Physics can have many discussions and so on, right? And well, that's just not true. For instance, what is interesting about all these papers, we have not found any evidence of data, you know, creation out of thin air. There are other papers. There's another retraction from Science that happened in the fall that we don't take credit for, but where the data were pretty much made up. But in this case, it was real data that was used to illustrate completely non-existent physics, right? And you can see how it's possible in the next slide. So the paper is in fact about the same signal, quantized Majorana conductor, says that PRL. And the first author of this paper is the last author of that paper. And so you can see here is in the paper, they showed these data, the orange data, and the sentence that accompanied these data. And this is just one of the figures, not even the main figure, but just to show you. The sentence is up there. Notably, the signal, the zero bias peak height, comes back up to the quantized value and does not cross through it. Now, right at the point where it was cut, it crosses through it and it goes to about 1.5 eventually. And just to put it in context for you, of course, the Majorana theory is incompatible with any signal that's above the red line. That's just not Majorana. And yes, it is possible that it's reduced, but it cannot be above, right? Just to make it simple. So we call it inappropriate data selection. You know, in this case, they just cropped, they chopped the piece they didn't like. This is a more famous figure from the same paper. It's a figure 1 or figure 2. And here I have to guide you, but the figure is in the upper left corner there, and there is a device picture, and the data is this merger of two lines. And you can again see up there that around 0.8 Tesla, my laser is dying, but luckily my hands are very long. So around this point, the signal again reaches 1 and kind of flattens out and does not go ever above 1. So this is what they highlighted as their, you know, the illustration of their claim. And however, they obtained tons of other data in very similar, in the same device and similar regimes, where if I look at the, thanks, now I'm going to be like Star Wars with, thank you. Yeah, so you look at these points here, and okay, you can also pull up the colors, but let me just tell you, it goes between 0.5 and 1.5, depending on which one you wanna put in that figure. It's all over the place. Now, there were only 2 out of over 20 that looked like this, and so all the rest were all over the place. And so what that tells you is there is absolutely nothing special in these samples about the value of 1. It can be anything. And therefore, we don't need to invoke the physics interpretation or the deep discussions of what it means. It's just misrepresented data, or it's a fabricated physics story with, selective data presentation used to illustrate a point that cannot be defended. And the same problem applies to an entire pattern of research from this group and at least one more group. Okay, so this is the substance of what happened. And now, in the remaining time, I will talk about how it made me feel, I guess, and what we can do better. So yeah, I would like to really highlight this event and all the other talks in this event, and because this is in principle a very technocratic event. They talk about how you use R and the databases and so on, but it is related to the year of emotional well-being at Pitt. And so I will talk about the data itself, but I also want to talk about the challenges that I and my friends who worked on this encountered as we set on. When I first found the first problem, it was from the group of my mentor, my postdoc advisor, a very important person for me. And my naive idea was that, well, I would sort of write it up, send it to him, and he will take care of it from that point on. And that's not what happened, right? So challenge number 1 is how much effort and how long it took to even just retract the one paper. I'm not going to read through all these points, but just look at the timeline, and the investigations of the other papers continue. They are still ongoing, but just look at, decision to make a retraction was made in March 2020, a few months after we found the problems. The retraction itself happened a year later. The investigation at the university wrapped up, not to our satisfaction, I must say, another year and a half later. So you have to have this patience and this sort of, on a human scale. This is like a significant chunk of my life that it took to just retract this one paper, right? Okay, challenge number 2. So we got the data for the first paper. We didn't get much data from the other papers. And this is sort of research integrity 101. If you find a problem, you ask yourself, well, is it just one paper or is it multiple papers, right? And because the physics was similarly flimsy, there is a whole set of papers. It's actually a longer list than this, where we wanted to see more data and were prepared to analyze it in a similar fashion. And we did get some data, especially from this Netherlands group. There's partial sharing. It's not satisfactory because you need really the full picture to assess the claim. You need full data. But they shared something, and I think it was a kind of a misguided effort to try to control the damage, the fallout. They tried to, sort of direct you towards, okay, we are happy to admit to these problems, so here's the data related to that. And then this other group, kind of the editor forced them to share a little bit on one paper, which was enough for us to conclude that the paper should be retracted. And then there's just stonewalling. They shared nothing since. And by the way, this slide is old, but the table still applies. In the past year, we got nothing. We got no new data that we haven't seen before. So this is how it goes. And of course, here I should make a disclaimer. This is from my Twitter. This is not a scientific poll, or maybe not fully appropriate to do in a high-level research seminar. However, people who read my Twitter a lot of them are scientists like me, professors, postdocs, graduate students in my field, quantum physics. And so this is an illustration, indication of, how they think about the problem, right? And so certainly if you ask them, they would say, oh yeah, sure. If you ask me for data, I will share it right away. But that's not what actually happens, especially when you have real concerns about the data. Now, challenge number 3. My group has done a lot of research where we looked into the validity of some of the claims. And it's not, always going out of our way, because, for instance, we're doing similar experiments and we see something that contradicts, and then we just need to write it up and, not be afraid or hold ourselves back from sharing some of the sort of negative results, right? And so we've done it a few times, and we are actually working on 1 or 2 more, but it's a big effort. Behind each of these papers is a graduate student or several students, a postdoc, that took the time to doing that, reproducing it. It takes months, if not years, to do it well, to do it properly. It costs money. Just to give you a ballpark, each of these physics papers is at least $100,000, if not more, worth of salaries and equipment, time, and so on. So this is if you really want to, if a colleagues would tell me, well, you disagree with this claim, do your own experiment. Fine, I'm going to do it. That means I'm committing a lot of resources to this. And finally, the final challenge. You do all this, and it can feel like it doesn't make a dent. Because the last author on this paper is the first author on the retracted paper. His data played a role in 2 of those nature retractions. It was based on his data. There were different collaborators, but he was the one that was in question. And the claim of the retracted paper was that the signal is at the value of 1, at the 2^²/h. And what we've proven and we've shown to all our colleagues, I gave these talks, and we put stuff online, and Nature wrote about it. I had an opinion in Nature, and all these editors, including at Physical Review Letters, attended our virtual events and were informed about it. And after all this, they publish the same claim, the debunked physics, where we said, look, the value is meaningless. In these devices, it can be below and above. It still comes out. In this journal that published Einstein and Feynman and Schwinger and, everyone, all the household names in physics. So, of course, not to be, empty worded. This is the data from their paper, right? And this is again the signal that is at 1. Wonderful, right? So finally they got it 4 years later. This is the data. Well, this is our data from my student, Ifan, from just a few months ago. And if I put my finger here, this value is about 0.5, and this value is about 1.5. So the visually the same signal, similar devices. And still, it's still not there, right? It's still, I can reproduce this shape if you give me enough time and my students enough time. Nothing has changed in the physics and the, our understanding of it. The only thing that changed is that this paper made it into physical review letters. And so from here, I can pivot to generalize. How did it become possible that this paper came out? What had to happen for this to happen, right? Now we can talk about it. I'm gonna again use my non-scientific Twitter to start to probe this question. So when this happened, I went to my followers and I asked them this question. So what do you think about physical review letters? Is it even a good journal? And you can see 430 votes. It's a good journal, according to my colleagues, for whatever reason, maybe you like the design of the cover or, all the reasons, on balance, is it a good journal? Yes. My community thinks this is a good journal. Okay, so then how could they publish that paper? So here's another one. Okay, so we know that this group has history, and so do you think it's okay to publish the same claim again? And well, it's an interesting. I think it's my own fault for phrasing the question this way because 30% said yes, but I think a lot of these people were basically reacting to the statement of fact. Yes, you do get to publish because it actually happened. So probably if I rephrase the question, there will be fewer yes and more no. So okay, so it's a good journal, but they shouldn't do this. Okay. Here's another one, okay. Here's another one. This was from a while ago, before the paper was published. This is from a year ago. I already thought about the possibility that, these people remain active in science and there could be a situation where they try to publish, and what should we do with this? And well, this one is an interesting one, right? Because there's a sort of a, at least a dichotomy, but suppose I get a referee request. Well, what, this group submitted a paper to our journal. Can you advise us? Okay, sure. I'm a responsible member of the community. I will advise you, but I know that this group is behind 2 retractions from Nature. It's extraordinary. So what do I do? Well, I thought, well, maybe I should withdraw myself because I'm biased by this knowledge. That's maybe an ethics question, right? Well, people don't think that's such a big deal that I know something about it. And another one here is interesting with just a few votes. I could reject it on fake grounds. So many of my papers were retracted. 0 of my papers were retracted. I do misspeak often, but they were rejected from physical review letters and so on for lack of impact. That's not interesting enough to the broad audience. So it's so easy to just, deal with it this way, right? Yeah, okay, this paper's fine. It's just not interesting. Well, actually, people don't think that's the way to do it, but they are split between these 2 options, and the winning one is review on its own merits. So, okay, maybe this is how the journal approached it, right? They received the submission. They said, okay, well, maybe there was a history here, but this is a new paper, and we can, we are armed with all our knowledge of the situation. We can review it on its merits. And so they sent it for review. And let me tell you, they did receive critique. Within the peer review process, they received critique. They just chose not to act on the critique. They chose to ignore the critique and publish the paper. Why they did that? Actually, I don't know, but bouncing off this poll result, which is not scientific and only used for illustration, I have a feeling that physicists, maybe also other scientists, they have this separation inside of them, that they see and they're subjected to all the unfairness of peer review and the politics and the need to get resources and all that side of the scientific. And then they try to separate inside of them that there is this part where this is sort of pure science, you know, the infallible, the truth that we sort of chip off. You know, it's like a painting that is covered, and we peel off the cover piece at a time and paint until the painting emerges. And we sort of try to keep these separate desperately, perhaps, or we put effort into saying that, you know, science will take its course. The scientists will rule. Eventually, we'll understand. We will take care of it. The system will take care of it. The process will take care of it. And I disagree with that. Having gone through this, I have taken some of these positions in the past, and I strongly disagree with them now. For instance, this second to last one is something I tried to follow early on. Like I told you, well, these people can claim what they want. I'm just going to worry about the science that is coming from my lab and make sure it's good. Which, of course, means my science doesn't get as far. My students don't get jobs at places like Tsinghua University. And, you know, people are sort of bypass this. And, you know, eventually I lose the resources to do my good science. Right. And just, you know, it's just suffocating when you go to a conference and there's all these claims and you sort of start to, you know, get physically worked up, like your pulse rises and so on. And you just feel like, okay, well, I guess I should just, you know, ignore it and just, you know, do the good thing. It doesn't work. You made your point, move on. Senior colleagues, respected, famous, told me this, you know, they understood, yeah, this was a bad paper. Yeah, but we're smart. We are famous and smart. We have prizes. We've authored famous works of theory and experiment. So yeah, we understand that it's not just this paper, but many others. So you don't have to repeat it to us. Just, you know, just, okay, you made your point. Thank you. They always start by, when I hear, thank you so much for doing what you're doing, that's like a code word for me. What's coming? What's coming is something like this, move on. Okay. Suppose I move on. Will physical review letters move on? This paper came out just last year, a few months ago. It's like nothing was learned. The point has not been made, right? So this will just continue. And the first two are sort of more philosophical, I guess. You know, peer review. I don't want to go into this, but it's a top topic for a whole other talk. But it's basically a waste of time. Papers don't change much upon peer review. What mostly happens in our field is paper gets submitted to another journal. You know, from Nature to Science, from Science to Nature Physics, from Nature Physics to Science Advances, to Nature Communications, and Physical Review Letters, Physical Review B, Physical Review X, Physical Review Research. There's a journal called Physical Review Research. What does it mean? What does the name mean? Oh, this is for research. And what about the other journals? I guess it's for, you know, what they publish. Okay. And this one is me trying to play an amateur philosopher, I suppose. There is a connection. I told you about this dichotomy. So inside of us, that there is a scientific process. It's how you do the experiment and you prepare it for publication. You publish it, you turn it into a grant, you graduate a student, you get a promotion. That's the process, right? That enables all of this. And there is a method, right? The search for truth, hypothesis-driven, verifiable research. And that idea is well-defined and pure. And my argument is that can be completely corrupted by how the process is run if the process is inefficient to a certain degree. So once the unreliable research amounts to a certain percentage, and I have not done the calculation or the research on what that percentage is, but I feel like in my topic, it's pretty high. The method itself is subverted. and science loses the ability to self-correct, because if the entire topic is wrong papers, the students learn to, perhaps trust them, or, at least partially trust them, and then they become professors and they teach their own students, and it can just run away. It just be a runaway process. Okay, so are you sufficiently depressed by now? Raise your hand. So now let me sort of cheer you up. There is a way, right? I see a way, and we're gonna go back to the data week again here. We went through ethics and philosophy and go back to data. There is a way which I don't know if we can solve human nature here, but at least we can make the process more efficient, more convenient, less, frustrating. And yeah, maybe physical review letters should stop moving physics forward. Just let it be. Maybe it should just let physics be. And so these are examples of physicists self-organizing to create these resources that make science so much more pleasant to do. And the famous one is arXiv. Probably all heard of the arXiv, and it spurred many other similar repositories in different fields, but it really came from physics. This is a data repository created by CERN, the European Physics Center. And this is our own niche, and there are examples that are better or more famous, but this is sort of our answer to physical review letters. This is a community-run journal, which I'm going to talk about next, I think. Yeah, it's called SciPost, and it's a bunch of professors, mostly theorists, that created this website. So what you do is you post your paper on arXiv, and then you send them the link, and they facilitate peer review for you, and then they still publish it like a journal. But what I really like is that peer reviews are public, and you can read them as they come. If I make a comment, it will appear after a check by a moderator. You can even know who wrote the reviews. So this is optional. You can stay anonymous, or you can publish your name. And by the way, Professor Pientka wrote a pretty critical review of this particular paper. And, he was still confident enough to put his name. So I'm grateful to him for this. And this is not my view of this website. You can go there and see all this information, right? So this makes the peer review process so much more meaningful. First, all this work by colleagues that read the paper is not lost. Suppose the paper is rejected. In physical review letters, you will not read what the people wrote. They may have made suggestions. You're not going to see it. Here you can see it. Second, they can be kept, kind of in check. I feel much more free to argue with my referees when it's in the open than when it's in the closed, but I feel completely enslaved to whatever they write. If they say, cite this paper, I'm going to do it. If they say, change this figure, I'm going to do it because I'm afraid. I want the paper to be accepted. And yes, we should be grateful to Pitt for supporting this one initiative. And I think eventually there should be a sort of a list of open science initiatives that the library should prioritize before they send another $5 million to, Nature Springer. They should perhaps support all these initiatives and then see how much money is left, because now it's the other way around. This is Zenodo. This is the CERN data repository. For each record, for each GOI, you get 50 gigabytes of storage. And in my group, typical total volume of data per experiment is 1 to 4 gigabytes. So we can dump everything. And that's what we do. We share our entire data and all the notebooks with the world. And, many people can do that. And, eventually it will probably be even required by the government. So I am done, but I still have 4 or 5 slides. another philosophical slide, perhaps. I really don't like doing what we now call science. I don't like it. But I also feel like it's unfair to call it science. This is not what I imagined science to be. When I was a high school student interested in physics, I thought this was science. Something like you do fun experiments, you share it with colleagues, you move forward, you make discoveries. And I didn't feel that I would have to calculate my H index for my promotion, or I have to butt heads with people who consider my request unreasonable, where the request is something like, I want to see your data because I suspect that you have data that contradicts your paper. Well, that's unreasonable. Okay. So why don't we stop calling this open science? Open science makes it sound like you have to opt into it somehow. Like, okay, I'm going to open up my science. Even the logo is kind of a lock. Have you seen the logo? It's a lock that's slightly open. The logo makes me anxious because I feel like this lock is going to close back any moment now. It's going to close on me and I'm going to be locked again, closed. So, this is closed science, and, we should just, be done with it, honestly. And there is hope, of course. Some of you may have seen this letter from OSTP, and the headline behind this letter is that, it's about making government science accessible to the public, but inside there is this statement about data. So going forward, December 31st, 2025, there will be a government mandate to share all data. So you better get ready for it. There is this NSF initiative to think about reproducibility. Just like a week after PRL published that paper on 5%, the 5% PRL, NSF came up with this. So there's good news. And finally, you've heard from me, but I'm not alone, thank God. And me and my colleague Brian Skinner from Ohio State put together this online workshop that's going to take place in a few weeks. And so if you want to hear from other people talking about this, still physicists, I encourage you to sign up. This is going to be a very interesting discussion. So this is, I think, the end of it. So thank you so much for coming.
We'll take a 2-minute break. So refresh says there might be some coffee left, and then we'll reconvene for discussion. So you can